Here I have a series circuit. I've got my power pack. Current flows out of the red terminal of the power pack, round the circuit through 2 bulbs and back into the black terminal of the power pack. It's called a series circuit because I have 2 components that the current has to go through both of them in turn. We can think of this like a TV series. In a TV series, the storyline continues through episode 1, episode 2, episode 3. The same story continues through all the episodes. In this case, we've got 2 lamps and the same current runs through them both. Like the storyline running through a TV series, we have the current running through first lamp 1 and then lamp 2. Oh, I've just messed up my connection, sorry. So these are connected in series because the same current has to run through both of them. I'm going to prove to you now that we've got the same amount of current at every point of the circuit by using my ammeter. I'm going to have to break the circuit so that I can run the charged particles through the ammeter. So now I've reconnected the circuit. It should light up any moment now. There we go. And we can see 0.05 amps is running through the ammeter there. I will reconnect the circuit here and show you that the current is the same the other side of the bulbs. Here we go, same tested again. Let the current run through the ammeter, 0.05 amps. All around the circuit, we've got the same amount of charge flowing through each second. That's what the current tells us. Now I'm going to test the voltage. Now remember, the voltage is the energy that is transferred. Now let's turn this to the right setting. We're going to have a different amount of energy transferred at different parts of the circuit. So if I compare the energy of a charged particle here to an energy of a charged particle on the other side, it tells us how much energy is transferred between both the bulbs. And we can see on the ammeter, he says, we've got about 10.7 joules per coulomb. So each coulomb of charge is transferring about 10.7 joules of energy as it goes across the 2 bulbs. Let's see how much energy is transferred going across just one bulb. Oh look, the voltage is between 5.7 and 5.9. My dodgy connections are making it jump around a bit. So only half the energy is transferred going across the first bulb. Let's see the second bulb. We've got about 5 volts transferred across the second bulb as well. So unsurprisingly, the total energy transferred across the 2 bulbs, the total voltage, is equal to the amount that is transferred as the charge passes through the first bulb, added to the amount that is transferred as it passes through the second bulb. So in summary, I'm going to call these lights 1 and 2. We can see that the current travelling through light 1, I, is equal to the current travelling through light 2. Because all of the charge that flows through one has to flow through the next because they're on the same path of the circuit. However, the energy that is the energy that's travelling through, and this is the same as the current at anywhere in the circuit. So I'm just going to write that as I on its own. Whereas the voltage across bulb 1 plus the voltage across bulb 2 is equal to the total voltage in the circuit. This is because the total voltage is all of the energy that's transferred by each coulomb of charge. Some of that energy is transferred on the first bulb and some of it is transferred on the second bulb.